I think we're going to start here. Good afternoon, and welcome to Blueprint for Clean Energy, a webinar speaker series hosted by the Yale Center for Business and the Environment. My name is Corey Amada, and I will be your host for today's webinar on thermal energy storage. The Blueprint for Clean Energy webinar series invites leading practitioners and researchers in the field of clean energy to talk about the latest opportunities and developments in corporate, nonprofit, and public-private arenas. Joining us today is Adrienne Little, Thermal Systems Technical Lead at Malta Inc., and Joshua McTigue, Research Engineer in the Thermal Sciences Group at NREL. Adrienne and Josh will provide an overview of thermal energy storage solutions, its deployment, and its potential to preserve grid reliability and balance energy demand as the global energy mix shifts towards renewable energy. Adrienne and Josh, it is a pleasure to have you join us today. We are so excited to hear your presentation. Before we begin, I would like to make a few quick announcements. First, the Yale Center for Business and the Environment is proud to announce the launch of our new website, so please check it out. And second, we would like to remind our listeners that we welcome any questions you have, and will direct them to our speakers at the end of the talk. Please type your questions directly into the Q&A window throughout the presentation. And with that, I would like to hand the presentation over to Josh.
Hi, Corey. Thank you. Let me share my screen. Okay, I can put the video on. So thank you for organizing this, Corey. Very happy to speak today about thermal storage for grid electricity applications. So as Corey mentioned, I'm a researcher in the Thermal Sciences Group at the National Renewable Energy Laboratory. As you can see in this picture on the first slide, we've got a concentrating solar power plant here, but there's also a molten salt storage tank, which is storing thermal energy. So we'll come back to that a little bit. I've got the title of the talk is Carnot Batteries for Electricity Storage. So Carnot Batteries is just one name for this type of system. So I'll come back to that again to describe where this name comes from. It's probably the name that you'll see most frequently in magazines and online. So I'd like to begin by giving a little bit of context about why grid electricity storage is a thing and what the requirements are for that. And then I'll go in to describe how Carnot batteries can really are suitable for this application, as well as giving an overview of the concept behind how they work and some history. In the second half of the presentation, I'd like to discuss a few of the different varieties of Carnot battery that exist, talk about some of the different applications, and hopefully give a flavor for the wide range of technologies that fall under this umbrella term of a Carnot battery. So to begin with, I'd like to talk about the grid a little bit. So you're probably very familiar with variable renewable generation and its intermittency. So here in the blue on this graph, you can see the wind generation in the UK in January 2013, and you can see it is quite variable. The other thing that varies, of course, is the demand for electricity. And you can see that in the UK and elsewhere in the world, there is a sort of daily pattern of demand. So clearly there is not a nice matching up of the supply and demand for electricity. So there are various different ways that this difference can be overcome, and energy storage is one potential solution. A graph that you often see is called the duck curve. This really shows the net load for a day in California, and it shows how that net load varies over the course of the day. And one of the very things you see very clearly is that in the afternoon there's a very sudden need for electricity. And so if we're thinking about solving these kinds of issues with energy storage, one of the first requirements is that energy storage has to be able to provide energy at a certain rate, at a given power to actually be able to be appropriate for this kind of problem. So the first thing we need to think about with energy storage is it has to have a power rating. The second thing to think about is when we're looking at this graph again, is that because wind power is variable, there may be days or hours where there may be lulls. So you're not being provided with the electricity that is required from that renewable resource. So for this same year, January for 2013 in the UK, for the wind power that was actually dispatched to the grid, you can do some analysis, and here I've shown a histogram which shows how long or the frequency of the length of the lulls that occurred over that year. So there's various ways you could define a lull, but in this case, I've just taken one example of that. And what you can see is that the vast majority of these lulls are less than maybe 24 hours, but maybe 75% of the lulls are less than 50 hours. So that's nearly 2 days. So if we're going to solve these kind of problems with energy storage, you need to have a certain energy capacity that can provide energy for a certain amount of time. It's also interesting to see that on this graph, there are actually some lulls that occur for nearly 250 hours. So there needs to be not necessarily energy storage, but there needs to be some technological solution that can solve these kind of very infrequent events. So if we look at this graph, which shows the power rating of different types of energy storage systems against their energy storage capacity, you can see there's a wide range of technologies that are currently available. But we're really interested in technologies that occur at the top right-hand side of this graph in the area where pumped hydro is illustrated. And we really want storage for grid applications to last hours, possibly even for days. So I'll talk now shortly about a few existing types of large-scale electricity storage systems, starting with pumped hydro. The concept here is very well known. Essentially, water is pumped up into a reservoir at a higher altitude where it is stored for a period of time. This water that can then be released at a later time and turn turbines to generate electricity. So this is the most widely deployed electricity storage system currently, nearly 180 gigawatts or so installed globally. It's got a very fast response, so you can respond very quickly to demand on the grid. What I think is quite interesting to note is that many of the US and UK plants were installed around 50 years ago. The story that you often hear in the UK is that between television programs, when there's a commercial break, everyone will get up and go and put the kettle on to make a cup of tea, and this sudden surge in demand could only be solved by, deploying these huge, building these huge reservoirs up in the mountains in Wales. So these kind of variations in demand, it's not a new problem, and there have been ways to solve this historically. Another energy storage system that's been deployed in a couple of examples is called compressed air energy storage. In this case, air is compressed and stored in an underground cavern. Now, there are 2 plants that exist, and again, these are fairly old, built nearly 30 years ago is the newest one, although there has been some discussion that a new plant, a large-scale plant might be deployed in Utah. So within that context, I'd like to introduce a Carnot battery. So the previous technologies, they converted electricity into a different form of energy. So in the case of pumped hydro, you were storing energy in the gravitational potential of water, and in compressed air, it's within the elastic potential of compressing the air. What we do in a Carnot battery is we take electricity and we convert it into a thermal potential, into a temperature difference. And you can do that with a machine called a heat pump that essentially creates a hot storage and a cold storage, and which is stored within some kind of material. That temperature difference is how the energy is stored. At a later time, that temperature difference can be exploited in a heat engine or a power cycle to generate electricity. And it's worth saying, I think, that heat pumps, heat engines, these are conventional technologies. These exist and have existed for a long time. So that the understanding of these types of machines is well understood, and really this is a new kind of application for this existing technology. So some of the advantages and why there's a lot of interest around Carnot batteries, well, first of all, they have fewer geographical constraints than pumped hydro or compressed air, which respectively require either sort of mountainous regions or the availability of an underground cavern. Of course, there will still be some geographical limitation if you're going to build a large storage plant, but those limitations are much reduced. Materials that are suitable for thermal storage also tend to be fairly cheap and abundant, and also can possibly be sustainably sourced. So materials I'm thinking of things like water, rocks, or salts. Another advantage is that thermal storage is also fairly well understood. It's been widely deployed within the concentrating solar power industry. And that, again, this diagram illustrates some molten salt. So that's liquid storage tanks. And you can see the scale of them from the guy standing on the top there. And these systems are also possibly modular and have some other advantages that we'll come back to. These aren't new ideas. The first patents are nearly 100 years old now, but over this time, these concepts have been reinvented several times. So in the 1970s, there was a sort of revival. In the 2000s, there was, again, further interest. It was reinvented simultaneously in 3 places, in the UK and France and Switzerland. Then in the 2010s, Entropic Limited began building a prototype, and there was some funding awarded to develop these technologies. And within the last few years, especially, there's been quite a lot of commercial interest. This isn't an exhaustive list. This is just a few organizations who've been pursuing this type of technology. And I'll come back and describe a few of these in the second half of the presentation. It's also worth saying that because there's been so many different organizations over such a long period of time reinventing this system, there are many names for it. There's just a wide variety of different even types of technologies as well, regardless of the name. I want to talk a little bit about where the name the Carnot battery came from. So Carnot was a French thermodynamicist. He laid some of the fundamental, or developed some of the fundamental principles of thermodynamics. And if we apply the fundamental principles that he developed to one of these thermal storage systems, so there's some thermodynamic jargon we can use to describe those kinds of principles, the main result that we find is that the maximum theoretical round-trip efficiency of the system is 100%. It's basically telling you all the electricity you put into the system, you can get out again. So this is, in some ways, quite a surprising result. And it sort of maybe is why the name of Carnot battery has been chosen, because it suggests that these systems can achieve quite high efficiencies. However, with thermodynamics, there's always a catch. No one's demonstrated a machine that can abide by these principles. So if you take into account the actual real world effects that occur in these types of machines, the efficiency decreases, and it's expected that a Carnot battery will realistically achieve round-trip efficiencies in the range of 40 to 70%. So we can compare that to other existing electricity storage systems to see whether that's any good. And you can see that's pretty comparable with compressed air energy storage. It's a bit lower than pumped hydro, and it's lower again than lithium-ion batteries. However, one of the advantages of the Carnot battery is it has a high energy density. So for a given volume of material, you can store more energy. Essentially, you have to buy less stuff to store your energy compared to pumped hydro and compressed air. Lithium-ion batteries have a very high energy density, but they're not considered to be so suitable for longer duration electricity storage applications. I've also put some costs. There's a cost per unit energy and a cost per unit power. If you recall, I was talking about the two sort of requirements of the storage. I'd say take these values with a pinch of salt. Obviously, all these technologies are at different stages. Lithium-ion batteries have been commercialized over the last 30 years or so, and their costs have decreased rapidly. Carnot batteries haven't been fully commercialized as yet, so those costs are somewhat approximations, although they are based on existing technologies. So I'm not sure if there will be such sudden rapid decreases in costs for these systems. For the pumped hydro and compressed air costs, well, compressed air, there's only been 2 plants built, so again, those costs are probably, it's just worth bearing in mind the kind of difficulties with trying to make these estimations for these kinds of systems. I also want to talk a little bit about the versatility of these systems. So as I mentioned, that electricity storage in a thermal potential, so that you also have heat and you have cold. So you have a lot of different things you can do with those three forms of energy. In terms of the storage materials, there are many materials that are suitable for thermal storage. There's many different ways that you can convert electricity into thermal energy, and many ways you can convert thermal energy into electricity. There's also some options for hybridizing these systems with other types of technologies. And as a result of this, there's a wide spectrum of different Carnot battery technologies that have been proposed, which makes it quite an interesting field. And hopefully now I'll just give a little bit of an overview to give an impression of some of those different types of technologies. I'll start off by discussing some of the commercial developments that have been occurring. So I'll talk about Highview Power's system and Siemens Gamesa. I won't talk too much about Malta, obviously, because we have Adrienne on the line who can really give a much better overview. And I'll also discuss the bottom figure here, which is Entropic's system. So starting with Entropic, they were one of the first developers recently of a Carnot battery. The approach they took was really to make as many innovations as they could to make the system as efficient as possible. So they were using rocks as the storage material, so quite a low-cost storage material, but they had some special innovations within the storage system itself to make it more efficient. They also used had made some innovations in the types of compressors and expansion machines that they were using in a bid to achieve higher efficiencies. They eventually ran out of funding in 2015, and their prototype was completed by Newcastle University and has been operated by them since. So that's one approach that can be taken to really go down the innovation route. Another approach can be, again, making innovations, but also trying to use existing technologies. So there's a similar system being developed by Malta. The difference really is in the thermal storage devices and the compression and expansion machines. So the thermal storage in this case is liquid storage using molten salts, which, as I described, has been deployed on a large scale in the CSP industry. The type of machines that are being used really benefit from being scaled up to large sizes, which is another difference to the Entropic device. There's another British company called Highview Power. They've developed a system called liquid air energy storage. This is quite an interesting system. It's actually a little bit like a hybrid between compressed air energy storage and a Carnot battery. Essentially, air from the atmosphere is liquefied to minus 196 degrees Celsius or so. I think that's roughly minus 321 Fahrenheit. Now, this liquefied air is very energy dense, so it's quite a compact storage, and again, relatively cheap. So Highview have also taken the route of trying to use as much existing types of technology that as they can to reduce the costs of deploying this. And they've got a plan that began operation in 2018, and that was also integrated with an industrial waste heat facility, again, to try and make some cost savings there. Another system that came online recently was developed by Siemens Gamesa. The approach here is again, to even more so, use technologies that already exist. So they're using rocks, which again are fairly low cost as the storage material, but in this case, they're just transporting them from the nearest quarry, so there's the limited transporting costs as well. To convert the heat back into electricity, they're using a steam turbine, so these devices have been around since the 1880s and are very well understood. So I think their sort of pilot plant came online in June 2019, and the plan is to demonstrate this technology and then make further developments and improve the efficiency. So there's a few different options here within the commercial space as into how best to actually commercialize these technologies, either go for innovation or use technologies that are already well understood. There's also a huge amount of research that's being undertaken within national labs and universities. So I'll just give a little plug to a couple of NREL projects. On the left-hand side, there's a technology investigating using very small particles, essentially sand, and heating those to very high temperatures, maybe even 1,000 degrees Celsius, which can then be used to drive a conventional combined cycle gas turbine. On the right-hand side, I'm leading a project investigating whether we can integrate Carnot battery type systems into existing concentrating solar power plants. So can you have a system that, again, making use of the existing knowledge of molten salt storage tanks, but also have a kind of combined system that can provide renewable electricity generation, but also provide electricity storage services. I'll highlight a couple of other projects that are occurring in Europe. So at the top here, there's an organization. They basically are quite interested in injecting the heat that they generate into the ground. So again, very low cost storage there, potentially. That heat can then be used either to generate electricity or also used for heating residential areas. So there's kind of dual purposes here, like a kind of using the fact that the Carnot battery system has both heat and electricity. And they also want to integrate with industrial waste heat systems. And on the bottom of this slide is a concept being pursued by the DLR, I believe. This is really trying to give a new lease of life to existing coal-fired power stations. So the idea is to retrofit these again with thermal storage, so molten salt storage tanks in this case. These tanks can be, this material can be heated up with electricity, so coming potentially from a renewable resource, and at a later time, that heat is then dispatched through the existing power station. So it's trying to find new applications for existing technologies, and in this case, existing infrastructure. So in summary, I've talked a little bit about the kinds of challenges with variable renewable generation, but also variable demand, and how electricity storage can be used to solve some of those issues. In particular, in this presentation, I've described Carnot batteries, which is a way of storing electricity in a thermal potential. These systems seem fairly promising in terms of their cost, efficiency, and sustainability compared to other large-scale electricity storage devices. And there's a wide range of different configurations and a wide range of different ways people are trying to commercialize these technologies. So it's going to be a very interesting few years as some of these systems are actually built and begin to operate and interact with the electrical grid. So that concludes my presentation. I'd be very happy to receive questions, discuss those at the end with Adrienne. And thanks for your attention, and thanks again, Corey, for organizing this webinar.
Awesome. Thanks, Josh. And I think now we're going to invite Adrienne to talk a little bit more on the commercialization side and the work that Malta is doing.
Okay, great. Let me share my screen. All right. Okay. So thanks, Josh, for a good background of different technologies out there and some of the theoretical basis and the different considerations out there. In my presentation, I'm going to make an attempt here to talk some more about customer needs, properties of markets, things that you have to consider when you're actually implementing and building one of these technologies. And so, you know, what we're seeing really is radical shift in how we're thinking about the electricity grid and how that relates to energy storage. And so, you know, I have this fun cartoon here. We've gone through many different ages. Now we're finding ourselves in the age of storage, where basically the cleanliness of our grid is really going to depend on what type of technical solution we find for energy storage. So moving on here. So Josh already mentioned or touched upon this in his presentation, the problem of intermittency. So basically, you know, we're starting to generate more and more power from renewables, from wind and solar, but the problem is that the sun's not shining necessarily when we need the electricity, and the wind is not necessarily blowing when we need the electricity from the wind turbines. And so we're getting to the point where we need an energy sponge of some sort on the grid to match supply and demand. And we're getting to the point where wind and solar are getting so inexpensive, in many cases cheaper than natural gas, where now we can add the cost of a storage system, and in that case, still be cost competitive with natural gas power plants. And so we're kind of at this tipping point of cost where we're seeing that this combined renewables plus storage system is starting to make not just sense in the terms of making a cleaner grid, but also making sense economically in terms of what potential future customers would want to buy from a lowest cost alternative. Another thing we're seeing is that with more and more wind and solar coming online, we're finding that these resources are actually being curtailed considerably. And what this means is that even if the wind is blowing, sometimes that wind turbine may be shut off simply because the grid cannot handle the input from that wind turbine. So if we want to be more renewable, more clean, whatever, it doesn't actually help us to install more wind turbines or more solar in some regions because they will simply be shut off. So really for that reason, storage is seen as kind of the holy grail or the keystone technology that's really going to enable further deployments of these sorts of renewable sources. So to give you some background on what we're working on at Malta Inc., this is a Carnot battery, like Josh was talking about, a different type version of it. And this was a project that started back in, let's say, roughly 2015, where it started at Google X and was incubated there for a couple of years, where there was a lot of scoping and technology scoping exercises. And then in 2018, we spun out as our own independent company outside of Alphabet, now known as Malta Inc., in which case we raised money from our lead investor, Breakthrough Energy Ventures, as well as some of our OEM partners. And so we're off to the races, and our goal right now is to build a 10 megawatt pilot plant with 10 hours of storage. And so whereas a lot of the issues and challenges we were dealing with previously were potentially more theoretical, more scoping, what types of technologies are we going to use, basic modeling, now we're really focused on, okay, we need to build a thing, but what is that thing supposed to look like? And how does it interface with the need of our customers? And so this is what I'll hope to cover in this presentation. So giving some background on our technology, we're really looking for a system that is essentially kind of the, let's say, the Swiss Army knife of energy storage. And by that I mean it's a technology that you can put anywhere and can be customizable to customer applications. So for example, Josh previewed pumped hydro. Sometimes we're seen as kind of like pumped hydro without the mountain, meaning that we can still store electricity, but we don't need a mountain to do it. Or we can be like compressed air energy storage in the sense that we can store electricity, but we don't need a cave to do it. So in that sense, we are site agnostic, and we can potentially be put in any location where the customer need is greatest. We also see ourselves as being cost competitive, and the fundamental reason behind that is that the base materials of our system are fundamentally cheap. It's things like steel, salt, air, etc. We're not using any rare earth metals or anything like that, or let's say complex clean room type of manufacturing processes that you see are needed for things like electrochemical batteries. Another big point of the Malta technology, but also many different Carnot battery technologies, many different thermal energy storage technologies, is that we're really leveraging existing manufacturing and construction ecosystems. And this is actually a very big deal. So back from my times at ARPA-E, we would usually say, how many miracles do you want to solve to get this technology to market? You know, there's already the technology, or there's already the miracle of figuring out the technology, but then there's also the miracles of, well, how are you going to make it? How are you going to service it? How are you going to ship it? All of these other things. So in a sense, if you want to get to market quickly on these sorts of energy technologies, you really want to focus on systems that can really leverage existing welding expertise, existing construction expertise, existing people in these different regions where they will be installed. And this actually becomes a very interesting social political issue, which I will touch on in a second. But anyway, so when you're looking at Carnot battery type of technologies like Malta, there's a lot of important features here that you need to focus on when you're looking at what type of energy storage technology you can deploy quickly to solve the problem soon, the intermittency problem soon. So on a very high level, you know, technically, what's the MultiSystem? Really, it's a different type of battery in the sense that it's electricity in when you charge it and electricity out when you discharge it. So we take electricity from the grid during charge, and then on discharge, we discharge electricity to power your washing machine or your light bulb or whatever. But we don't look like a lithium-ion battery, or we don't look like a typical battery, because our battery isn't full of chemicals. Rather, it's full of heat exchangers and rocks and salts and these sorts of things. And so if we dive another level deeper into what's actually happening in our Malta system, on the left here, we have what our charge mode looks like. So essentially what we have is a closed air Brayton cycle. So we have air flowing around in a loop. And in this loop, we circulate that air with what we call turbo machinery, a combination of a compressor and a turbine. And so what this does is, this is what we call a heat pump, and it takes electricity from the grid to produce a temperature difference, much like what Josh was mentioning in his presentation. And so when we produce that temperature difference, we store the hot side in molten salt, and that's the 2 tanks on the top here. And then we store the cold on the low side here in 2 other tanks that are shown on the bottom here. So that's our charge mode, again, taking electricity from the grid and using it to produce a temperature difference and storing that temperature difference. Now, then we wait until electricity is needed on the grid once again, and then we switch the system to discharge mode, where we essentially operate the system in reverse. We still have that closed air Brayton loop with the turbo machinery running, but in this case, we're sucking heat from our molten salt tanks, and we're using the cold, so to speak, from our antifreeze tanks, and now using that temperature difference to generate electricity and sending it back to the grid. So if you want a nice analogy here, for those of you who are maybe less familiar with thermodynamics, when we charge the system, think about it like a giant refrigerator. What you do with your fridge is you plug it into the wall, and you use that electricity to make the inside of your fridge cold. At the same time, the back's getting hot. We're doing the same thing. We plug our system into the wall, essentially, and we make hot and cold. Then in discharge mode, we're like I guess the analogy would be kind of a standard power plant. You burn fuel to produce heat. And when you do that, you can produce steam, usually, that spins a turbine, and that spinning produces electricity. We're doing a very similar thing here, but with air instead of steam, and molten salt instead of burning fuel. So that's kind of the technology at a mid-high level, depending on what your background is in thermodynamics. But fundamentally, you know, what we're looking at here is a system that looks a lot like, it's a big system. It looks like a combination between a chemical plant and a standard power plant. And what we're trying to do is we're trying to use existing technology that's available in industry on the hot side for our molten salt tanks. And here we can pull directly from technology developed and already used in industry, in the concentrated solar power industry. On the cold side, we're looking at temperatures that you typically see in potentially LNG or air separations technologies. And then in the middle, with our turbo machinery, with our spinning bits, we look a lot like gas turbines. So really, we see this as kind of a patchwork of existing technologies and existing competencies all being brought together for a new application. And, you know, again, this slide here is a little bit of a repeat of what Josh already showed, but basically showing how Malta compares in terms of other energy storage technologies. And, you know, if you look in this region here, you see a lot of competition at the smaller power ratings and the short discharge times with electrochemical batteries. So these are the type of batteries like lithium ion that you're more familiar with. But when you need really big power shifts, really big systems to balance load on the grid for hours at a time, there's less options available. And so this is where Malta and Carnot Batteries play. And again, emphasizing that really, you know, Carnot Batteries and Malta are one of the few solutions that can play in this space and not require geographical features like mountains or caves. So really, it's one of the few technologies that you can make big systems like this and put them anywhere. And so a few interesting things to mention with technologies like Carnot Batteries, this also applies to flow batteries, is that you can think about these energy storage systems as being, you think of them as like 2 different parts. So if you think of your car has an engine, and then your car has a gas tank. Now the engine dictates the power, essentially how fast you can accelerate, let's say. Whereas the gas tank is for how long can you drive. So in the case of a Carnot battery, we have our engine, our power block, and then we have our gas tank, which is essentially our molten salt tanks, or in the case of what Josh is working on, rocks or solid storage, but tanks. And you can tailor the size of these two bits to your customer needs. So if you need to charge faster, well, you make a bigger engine. But if you want to discharge for longer, 10 hours, 20 hours, 40 hours, you make a bigger tank. And so what this means is that when you look at energy storage technologies, if you're looking at a lithium-ion battery, typically what you see installed is something that will discharge over 4 hours. And you don't typically see them installed for durations of 4 hours and longer, is because they're too expensive. But if you have a system where you can decouple the engine and the gas tank, like a Carnot battery, you find that at much longer durations, usually around 6 hours or longer, it starts making a lot of sense from a cost standpoint to install something that looks like a Carnot battery, because you can have the same engine but just make the tank larger and larger and larger, and that's relatively inexpensive. Other things we're looking at here is in terms of looking at long asset lives. One word of caution when you're looking at comparing cost of different energy storage technologies, make sure you're looking at what you call the full balance of plant cost. So for example, if you look at a lot of lithium-ion battery costs, you're just looking at the battery pack. You're not looking at all the power electronics, AC/DC converter, connection to the grid. That's what we consider kind of the full balance of plant. When you're looking at lithium-ion batteries, make sure you get the full picture. And same thing with if you're looking at a Carnot battery technology or pumped hydro or whatever, just make sure you're getting the full system costs. Often with electrochemical batteries, they just cite the pack cost. But anyways, looking at 30-year asset life, another good question to ask when you're evaluating these technologies is how long will it last? With existing battery technologies, your battery pack might last, I don't know, 10-ish years with existing available technologies. But with things with Carnot batteries, you're just heating and cooling salt or rocks. And so you don't actually degrade the system when you charge and discharge it. So you can really truly get these 30-year lifetimes on these sorts of plants. Flexible deployment, site independent, variable normal. Okay, I covered those things. So, you know, in terms of what Malta is doing, again, we're really looking at a concept that has kind of the fundamental technology figured out already, and then using those existing manufacturing ecosystems. And so what this means is we really see this as an implementation challenge. How do we get the resources we need to build this first of a kind sort of plants? And this is what I call an implementation challenge. And so one thing we think about in terms of implementation challenge is what are we going to build? And so we typically look at what we're going to do in terms of two buckets. One is a smaller thing, a 10 megawatt pilot plant, and also products potentially, and then also looking at 100 megawatt size. And these different sizes serve different markets. And you know, as we talk to different customers, they give us feedback on what types of things they need for these different markets. So for example, on the small side, we might be looking at something that's a little bit more nimble, that's going to go on an island grid, for example, or maybe critical backup for a data center. But the big ones are probably going to play more in wholesale markets, load shifting on big grids, potentially things like, well, definitely in places like vertically integrated utilities and such. And I like this cartoon here because this is something that we think about, you know, on a daily basis. Is we're going to build a first thing, a pilot plant. But how do you decide what a pilot plant is going to look like to prove what you need to prove to your customers and your investors, et cetera? And so often what you're looking at is something like a staged approach, kind of on the bottom of this cartoon here, picking the critical features first for pilot plant, but then adding features as you go along that will make the customer happier and happier. And so this actually factors a lot into the engineering and design process of a pilot plant versus a product. Okay, So I've talked a little bit about Malta, basic technology, the types of things we're thinking about. But how does this technology and Carnot Batteries generally, or other types of energy storage, what are we looking at in terms of markets? And what do we have to think about when we're thinking about product development, let's say? And so I'm going to give you a snapshot of a few different things we're seeing, just food for thought. But basically, let's say the storyline here is that, again, we're seeing more and more intermittent renewable energy coming online. And that's redefining how the grid is operated. Josh mentioned the duck curve. We're seeing these incredible ramp rates up and down on the grid. How are we going to deal with those as we see essentially an exacerbation of the process with more renewables? And so because we're seeing these crazy ramp rates on the grid, we find that customers are developing new needs. They have new problems, new things that they have to adapt to. And so now when they talk about energy storage and what they need from energy storage, that's constantly shifting. And so what that translates to is markets are being redefined, both in terms of technically what do you need to build to help them the best, but also from a political standpoint, from a regulation standpoint, we're seeing an incredible change in how the electricity markets are regulated and how you value the different services of generators on the grid and storage on the grid. And so I'll touch on all these a little bit, but this is mostly just to give you a taste of the things we're seeing. And so one thing we're seeing is that, again, the grid is changing substantially. And so there's two kind of important things I wanted to highlight here. Well, three, I guess. So first, electrification can be expected to increase, especially if we have increasing adoption of electric vehicles or electrification of industrial heat processes. So we can expect demand to increase. We're also seeing that fossil fuel generation is in low demand. So this means there's a lot of coal plants going offline. There's a lot of nuclear going offline. Depending on the country, you could be in pretty bad shape right now with your baseload generation. And by baseload, I mean this is kind of the reliable, kind of steady state base electricity that's always on and always there, whereas the wind and solar are kind of on top, playing around. And so what's happening is that baseload is essentially going away. And there's kind of this gap, and it's like, oh, what are we going to do if we don't have that reliable base load? And on the image here on the bottom left, I thought it was just kind of a nice illustration of a European example of all the different fossil plants, coal plants, that are 30 years and older and that are less than 30 years and older. So these are all physical sites that are going to be potentially decommissioned or downgraded due to emissions concerns and political initiatives, I should say. And so this is kind of where the social political aspect comes into play. There's going to be a huge amount of people in all of these locations and all these countries that are simply out of work. And so if you can find a technology that looks a lot like a coal plant, for example, a MultiSystem, a Carnot battery, then you could use all of those existing workers, all of that existing expertise, and essentially plop these sorts of technologies right in these locations where you have all the existing infrastructure, or a lot of the existing infrastructure there and ready to go. Another big thing we're seeing is that wind and solar plants are on back order. This here is a graph with projections of wind and solar installations and showing that fossil installations are much, much less, if not zero, in many locations. So it's almost like a perfect storm of all the base load going away and us not really being able to replace that base load with anything that is consistent, let's say. That's the role that storage has to play. So actually here, I wish I could show one of Josh's graphs again. He had shown how there's different lulls in wind and solar. And typically those lulls are maybe on the order of hours or a day or something like that. But there are some times when there's absolutely no, or bad solar resource and absolutely no wind for potentially a week or much longer periods than one day. And so when you're talking to customers, especially utility customers, what's really key to them is reliability, reliability, reliability. So even though a given system may work most of the time, maybe 90% of the time, maybe 95% of the time, utilities still have to prepare for that 5%, that little bit of time where there's no wind and no solar, and make sure that the grid can still run under those conditions. And this is actually a major pain point for utility customers. So that's one thing. Another thing is this image I'm showing on the right here, which is, if you look at the different rows here, frequency response, reactive power, inertia, blah, 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 these are all kind of different features, let's say, different specs of a given asset on the grid. And so what we're seeing is that the thermal assets here, these are the ones that are typically going offline. Our grid was based on systems that have these features, frequency response, reactive power, blah, blah, blah. And now that they're gone, there's actually kind of this gap in need where we need systems that can still provide these services. But things like solar certainly do not provide those services. Things like wind kind of provide those services, but otherwise we don't have a lot of good options. And so again, with a MultiSystem or a Carnot battery, you're servicing a lot of these needs on the grid and filling in these gaps that are starting to appear because there's more wind and solar. So this here is just kind of a nice image of what happens on the grid and why it's important to have all these different features like inertia, for example, on the grid. And so this is just showing what's happening to, so this is the grid frequency, nominally at 50 hertz, at least in Europe. And so what happens when you have a sudden outage or unexpected, let's say no wind suddenly or no sun suddenly, is that one of your generators will go offline and there'll be a sudden dip in the frequency of the grid. And so what needs to happen is that there's a series of events or a series of assets that come online to solve this problem. So for example, one asset would need to respond in a half-minute time frame. Next asset would have to react in a 5-minute time frame, 15 minutes, and then essentially your base load comes online at that point. And so a utility customer is looking at, okay, I'm going to buy a thing, but what does it service? Does it do all of these things, the pink, the orange, and the red, or does it only do one? And so they have to have an appropriate asset mix and appropriate features of their systems to deal with problems like this and ensure that reliability. So I just thought that was kind of a nice illustration of what the utility customers or microgrid customers are dealing with and what's informing their purchase decisions, let's say. And so another point I wanted to make was with storage, I mentioned that the markets are shifting completely because the needs are shifting completely. And so typically in the old days, let's say, and by old days, I mean maybe a couple of years ago, storage was typically seen as something that would perform arbitrage. And what that means is you buy electricity when it's cheap, when there's excess, and then you sell it later when it's needed. And so you make a profit in that way, buy low, sell high. But now we're seeing more and more needs for storage and more opportunities for revenue. So one that I like to point out is, for example, transmission and distribution. So we're seeing in a case now where we used to have these centralized coal plants, those are going offline, and now you have little wind turbine plants dotted all over the place. So if you think about the grid as like a spider web or a network, the shape and size of that network is changing a lot because now it's feeding more distributed sources instead of just servicing one central resource. And so what's happening is there's a tricky issue of NIMBY, not in my backyard. It's very difficult to build new power lines, new assets, new sites, etc. And so in some cases, if you can put a storage asset at a specific or critical node in the grid, in that spider web, in that network, you can actually stop investment in new transmission and distribution infrastructure. And so that in itself starts to become a revenue stream for storage. So that's just one example, but this slide is listing a bunch of other different features that storage has and markets that they can play in. And so one of the key issues that storage technologies are seeing now is how do we predict how much money we can make? No one has really put a dollar value on transmission and distribution deferral, for example, but we can take a guess. And there's a bunch of other things. How do you price reliability? you know, we want to have a reliable grid, but how much is someone willing to pay to ensure reliability? And so this is part of the issue we're dealing with now. And so in conclusion here, I thought I would throw up 2 books that I read recently that might be good for people that are looking to learn more about energy or about the grid generally. On the left here, The Grid by Gretchen Backe is good for people that are, let's say, not super familiar with the challenges on the grid, but I think does a good example giving a background where you can learn enough to be dangerous in these sorts of conversations on what is needed on the grid. And of course, there's a lot of discussion in there on energy storage and the role it has to play. On the right, Richard Rose is a fantastic author. He wrote this book, Energy, A Human History. This is less related to storage, but also a good book to read. It kind of tells the history of humans, let's say, or the history in the last couple hundred years from the lens of different energy technologies. So how did electricity generation change human society? And how did human society affect how the electricity grid was built and things like that? So that's kind of a fun read as well. So I will leave you with that, and I think it's probably about time to go to questions.
Awesome. Thanks, Josh, and thanks, Adrienne, for the presentation. I think it was really informative on a different type of storage solution. And as mentioned, I think now we'll jump into the Q&A. Just as a reminder to everyone on the webinar that you're welcome to throw in questions on the Q&A tab on the Zoom platform, and we'll address them. Just to start off, though, Adrienne, you mentioned a little bit about the response time for thermal energy solutions. I was unclear on one point. For thermal energy solutions, is it a fairly quick response when energy is needed, let's say on the grid, or is there like some type of lag time to ramp up to energy discharge for the system?
Yeah, that's a good question. Now, when you're looking at Carnot batteries and MultiSystems and things like that, you're looking at things that can respond kind of like a gas turbine power plant. And so this is typically going to be on the 5-minute time frame from when you can go from like a 0 load condition to a full load condition. And so that is helpful for some cases, but it doesn't fully solve the entire problem, because you're still going to have that issue of 5 minutes, which is actually a very long time on the grid standpoint. So in reality, what you're going to need is probably, if you're looking at this from a full grid standpoint, you're going to need some sort of combination of batteries, like lithium-ion batteries, and bigger things like Maltas and Carnot batteries. You can kind of think of batteries as the quick sports car that can ramp up really quick and get you there. But you can think of things like Carnot batteries and MultiSystems as kind of the big, lumbering, reliable giants, maybe the Hummers of the grid. And so in the end, you're looking at time scales from milliseconds to minutes, let's say, or hours. And so really different technologies are suited for different aspects. But in terms of what's needed today, I think it's fair to say that lithium-ion batteries are fairly well developed or mature. And so they are able to provide those quick millisecond types of services already. Now the critical need is the big lumbering giants, the load shifting, the big Carnot batteries and Malta type of systems. That becomes the critical need today.
Awesome. Thanks for answering that. Maybe for another question, either for Josh or Adrienne, can you talk a little bit more about maybe the environmental impacts of, let's say, either the molten salt or the disposal? I know you both mentioned that there's approximately like a 30-year asset life, but after that time frame, is it both the salt and, let's say, the storage facility that needs to be renewed, or is there just one of the two that has to be restored?
Mm-hmm. Yep, I guess I can jump in for that one as well. So these systems, these Carnot battery systems are fairly benign. So in the case of molten salts, there are some minor emissions that come when you first start the plant. but once you've gotten past that first commissioning phase, there's near zero emissions coming from the plant. And then in terms of end of life, so this is actually a very important question because life cycle analyses for these different technologies are important. Like with lithium-ion batteries, no one really knows what's going to happen at end of life and how they're going to be recycled. In the case of Carnot batteries, I guess I can speak to molten salt. The molten salt, the salt itself is actually what they use as fertilizer on crops. So at end of life, you could actually repurpose the salt for that use. But for everything else, you know, the pipes and the valves and the metal and the turbo machinery and things like that, I mean, in many cases, you can sometimes repurpose directly the heat exchanger for another application, or sometimes you can melt them down, use the steel for a different process. So we're not really looking at any nasty chemical leaching processes that might cause environmental issues from a life or recycling standpoint.
Okay, and then
yeah, I would.
Sorry, please go ahead, Josh.
Sorry, I would support everything Adrienne said there. I think maybe there's also some impacts to think about in terms of the sourcing of the materials, where they come from, or how they're generated. That often has some impact as well. To talk about maybe things more generally, it really often it'll depend on the type of system that you're trying to develop and what kinds of materials end up being in that. Because these systems are looking at very large scale energy storage, that typically means that you want a very low cost storage material. And so the types of things that tend to be low cost tend to be fairly sustainable compared to being a more complicated kind of chemical or something more exotic. And that also goes for the machinery. If you start wanting to go to very, very high temperatures, for example, you're going to have more exotic metals going into that machinery, but that will have a significant cost impact. So at the moment in this phase of development, when costs are really one of the most important factors for developing these technologies, it naturally ends up that the materials being considered have a less significant environmental impact.
Awesome. I think we have time for one more question. I think, you know, just maybe it's more so in the regulatory environment. Are there anything that you think that are either helping or maybe hurting thermal energy storage deployment, and anything maybe on the horizon that either of you are particularly excited about?
I guess in terms of helping, I think recently there's just been increased awareness that we need to treat storage assets differently than we treat generation assets. FERC Order 841 in the US is one example of this. Each state has to come up with how they want to value storage assets. That being said, it's great that people are starting to think along those lines, but there's still a lot of work to be done. And you know, this is kind of what I was saying of how do we value all the different things that energy storage can do, and how do we value it also in the future where we don't really know what the grid is going to look like. And so in terms of things that potentially hurt, we do see some policies coming out that where the policy looks or supports a technology that looks like a lithium-ion battery. So for example, it might only allow systems that can discharge in 4 hours, or have a certain energy density or something like that. So in many of these cases, we need to be careful that we're writing policies that are inclusive of all different technology types, compressed air, flow batteries, Carnot batteries, blah, 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 so that we aren't artificially restricting the technologies that are available to us to solve this energy storage problem.
Okay, so I think that's all the time we have today. This concludes today's talk with NREL and Malta on thermal energy storage. Adrienne and Josh, I'd like to extend a thank you for joining us today and for the presentation. It was extremely informative, and I had a great time listening. We also want to thank the Blueprint audience for all your questions. And as a last note, to view a recording of this webinar, please visit the Events tab on the Yale Center for Business and the Environment website, or access the recording through CBA's YouTube page. This will conclude the webinar, and thanks again for joining us.